And welcome to the last video, Chapter 2. We're going to talk about the normal distribution and actually do some calculations with it with something called the empirical rule. So we're going to be using this diagram later on towards the end of the video. First, some additional information about normal distributions. All normal distributions or normal curves have the same overall shape. They are all, um, come on, there we go, symmetric, okay? They are single-peaked and bell-shaped. So every time we draw a normal distribution, it should look something similar to this. It is symmetric because we could cut it down the middle, and it's the same left as it is on the right. It is single-peaked, hello, and it is bell-shaped. A specific normal curve is described by two features, and that is our mean and standard deviation. Now we're going to start using more of the population mean and population standard deviation symbols, which are our mu, which again just looks like a U with a little curly front there, and standard deviation, which is our sigma, lowercase sigma. It kind of looks like an O with a little curly Q coming off the top of it like that. Okay, so anytime you see these two symbols, we're talking about mean and standard deviation. The mean is located at the center of the symmetric curve. Okay, the mean would be located right here. It's always right in the middle, and is the same as the median. Since the distribution is symmetric, the mean and the median are both located right in the middle. Since we have zero skewness, then the mean doesn't really go one direction or the other. Now, here example of two normal curves. They're both bell-shaped curves. They are both single peak. They are both symmetric. But there is a little bit of a difference between them, as you can see. All right, so question here is, what would happen to the following two curves if you increased, let's say, the mean, but not the standard deviation? All right, so if we were to increase the mean, think of this as a number line, yada, 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 and let's say this is also some number line, where mu is just at some particular value, then if we were to increase it, really all we're going to do is move the curves down the line. Okay, so the curve will shift to the right, but there will be no change in spread. They'll still be spread out the same amount. If we were to increase sigma, if we were to increase the standard deviation, the spread, but not the location of the mean, then you can think about, well, really, this is going to start stretching out further this way. This is going to start stretching further out that way. This is going to stretch out farther. This will stretch out farther. But the location of the mean will stay right where it is. Basically, these two curves are just going to get shorter and fatter. So we'll become more spread out wider, but no change in the center. That center is still at that specific value. Which has a larger standard deviation, a larger spread? Well, I'm showing you, here's an example of one standard deviation in this normal curve. Here's one standard deviation in curve number 2. So obviously number 1 has the larger standard deviation. It has a wider spread to it. How many different normal curves are there? Well, I mean, here's two examples. So there are really infinitely many normal curves. It depends on what the mean is, depends on what the standard deviation is. If there's infinitely many means and infinitely many standard deviations, then you can create infinitely many normal curves. The shorthand notation for normal curves looks like this. It's a capital N, there we go, and then parentheses, then you write in whatever the mean is, comma, whatever the standard deviation is. So this capital N is just telling you were dealing with a normal distribution with this mean, whatever specific number that is, and that standard deviation, whatever specific number that is. Now, one other thing I want to show you before I flip here is, how do you know how much a standard deviation is depending on the shape of the normal curve, whether it's shorter and wider or it's taller and skinnier? Okay. Imagine you're skiing. Skiing. Here's your skis. Here's your arms. And let's get a different color here. Here are your poles to help you ski. Imagine you're going to go down this slope, okay, this normal curve. When you start to go down the curve, you're going to start to accelerate, and you're going to get faster and faster. Your acceleration is going to increase. Eventually, you're going to hit a point in the curve, okay? It's not exactly halfway down, though it may oftentimes look like it's about halfway. But right about in this vicinity, This is where, and if you're in calculus, this is specifically called, what is this? Like this is the second derivative. This is where the acceleration starts to not increase. Once you hit this point, you're not going to be going as fast as you were when you first started skiing. You might maintain velocity, but your acceleration is decreasing at that point. All right? That is about the location of a standard deviation. And then if you take that distance there and duplicate it, maybe that far, there's maybe another one of those sigmas, then right here, that would be 2 standard deviations away from the mean. And if we duplicated that distance again to the best of our ability, there's another standard deviation. Here now you're 3 standard deviations above the mean. So likewise here, imagine you're skiing down, you're going to hit a point maybe right in this vicinity where you're going to stop gaining speed. And that distance there is a standard deviation. If we try to duplicate that width there, there's another standard deviation, and here's a third standard deviation. And we can do the same thing on the other side. Here's one standard deviation below, there's another standard deviation below, and another standard deviation below. So that's how you can estimate exactly where a standard deviation is in a normal curve. Okay? Find the first one on the left and the right. Since it's symmetric, they'll be both about the same location. These 2 points here should be the same distance apart from the mean right there. And then you can just do it symmetrically on the right as it is on the left. Okay. Standard normal distributions. Now, standard normal distributions are very special. They have a mean of 0, which means here's our mean right in the middle. It is 0, and we have a standard deviation of 1. So when we want to go 1 plus 1 standard deviation above the mean, we're currently located at 1 on that normal curve. If we want to go up another standard deviation, we're going to be now at 2 standard deviations above the curve. Basically, these numbers here, and I would highly recommend writing this on your notes right now, those are really z-scores. Okay, those z-scores where we would take a certain value, subtract away the mean, and divide by the standard deviation. Whenever we would get, let's say, 1.5 as a z-score, well, right there is about 1.5. That's saying that you're 1.5 standard deviations above the mean. That means you have this many people that did worse than you, and you have this many people that did better than you. Okay, so that's just something to keep in the back of your mind. We're not going to do too much work with the standard normal distribution, but just know it is something specific. So this would be the shorthand notation for a standard normal distribution. It'd be the capital N for normal distribution, the mean is 0, and the standard deviation is 1. Now, with the next thing we're about to do, we're going to start getting into more calculations. And there are tables in the back of your book that give you specific z-scores to tell you the percent, or really the proportion area under the curve at a certain z-score. We're not, in elementary stats, going to use really this table at all. In AP stats, again, not really going to use the table. So I will mention in class, I'll show you how to use it a little bit more in class, but really if you're Amish, that's about the only time that you will have to use the table. You'll always have a calculator which can easily calculate, for example, this number right here. I will show you in your calculator how to get that number without having to go and look it up in the back of your book in a table. All right, now let's do some calculations. So we're going to do some very specific calculations with something called the 68, 95, 99, 7 rule. This is one way of referring to this rule, or you may call it the empirical rule. So the 68, 95, 99, 7 rule or the empirical rule. They mean the same thing, okay? So the nice thing about normal curves, and it doesn't matter what normal curve you're referring to, whether it's a short and skinny or a tall, or no, short and fat and tall and skinny normal distribution, there's something always that's true. And that is about 68% of all your data is within 1 standard deviation of the mean. So 68% of observations fall within 1 standard deviation of the mean. And now we mean 1 standard deviation above the mean and 1 standard deviation below the mean. Okay, this much right here, because remember we said the area underneath any density curve, including normal curves, is 100% or 1. Well, here's about 68% of the 100% right here. If you were to go down and up 1 standard deviation, there's about 68%. It's not an exact thing, it's an approximated thing. 95% of all observations will fall within 2 standard deviations of the mean. So if you were to go down and up 2 standard deviations, plus 2 sigmas and minus 2 sigmas, that between here and here, underneath your curve, which would be all of this, that's about 95% of everything. All right? And then last but not least, 3 standard deviations above and below means you have 99.7%, again, approximate 99.7% of all your data. That means that 0.3% fall beyond 3 standard deviations in a normal distribution. Okay? That means if this is you sitting out here, more than 3 standard deviations above the mean, we're talking genius territory. If, on the other hand, you're down here, you're 3 standard deviations below the mean, and we're talking about IQ, you might be in an institution or some sort of special class. So let's try a few practice problems here. Okay. The blood cholesterol readings of a group of women follow the normal distribution with a mean of 172 and a standard deviation of 14. Within what range do about 95% of the readings fall? Okay, so our mean, and I'm always going to label the middle here as always the mean, and it's at 172. Now 95% we just mentioned is plus or minus 2 standard deviations from the mean. Okay, so if I drop down, and again, let's use that approximation for how to calculate 1 standard deviation. I'm going to say it's about right here and here. Okay, there's minus 1 standard deviation. Here's plus 1 standard deviations. So about right here and here. Now a standard deviation is worth specifically 14 blood cholesterol readings numbers. Well, I don't know how that follows, what the units are here that we're talking about. So if I were to take 172 and subtract 14, I would be at 158. And that would be specifically that number right there in the normal distribution. Okay, 1 standard deviation below means I'm subtracting 14 from my mean, and I would be at 158. Now, I need to go 2 standard deviations, so I need to drop another sigma or another 14. So now if I subtract another 14 from 158, I'm now at 144. So 144 is the equivalent of 2 standard deviations below the mean. They're looking for a range though. So I know the lowest blood cholesterol reading I could have and still be considered in the middle 95% would be 144. And we can go up to, now we need to go on the right side and figure this thing out. Okay? So this specific number right here, that would be 172, and now I'm going to add a standard deviation. So now I'm at 186. Again, that's the equivalent of 1 standard deviation. But I need to go another one. So I'm going to add another 14. Oh, where am I at here? Add another 14 to my 186, and now I'm at 200. So from 144 up to 200, that covers about 95% of all of my group of women here that follow this specific normal distribution that have a mean of 172 and a standard deviation of 14. All right, let's try another one here. So I'm going to erase all this. I know I only put one normal distribution there on your paper, but you can draw another one real quick. About what percent of women have readings between 158 and 172? Well, 172, that was the mean. So I'm going to put that back here. And 158, that's below the mean. Well, how far below the mean is 158? Well, let me subtract that here. I've got to borrow 1 from 7. This is 158 is 14 below. Well, is there anything special about that number 14? There is. It's 1 standard deviation below. So if I were to drop down 1 standard deviation, There I am at 158. And the question is this: what percent of women have readings between 158, let's make this a little smaller here, between 158 and 172? I need to figure out what is the area underneath the curve, underneath the normal curve, from 158 to 172. Well, here's the thing. If I were to go one standard deviation above the mean as well, which I don't want to do, but one standard deviation above and below, well, that was 68% approximately according to our empirical rule. Now, since the normal curve is symmetric, that means these two areas here, this area and this area, are the same. So if I take my 68% and divide it in half, because I only want the lower one standard deviation, that means I'm looking at about 34% of women have readings between 158 and 172. Okay, this is the answer we're looking for, the 34%. Part C, readings higher than 200 are undesirable. About what percent of readings are undesirable? So let's, again, erase this. We can put our mean back at 172. Now, 200. 200 is going to be bigger than the mean. How far away is 200? Well, if we subtract those two things, we get 28. So it's a 28 away from the mean. But now if I divide that by my standard deviation of 14, that's telling me I'm 2 standard deviations above the mean. So here's maybe 1 standard deviation. Here's 2. So that specific number again was 200. They want to know now what is the percent that are undesirable. And undesirable means higher than 200. So we want to find the area under the curve that's beyond 200. All these people right here that have 200 and up. All right, so to do this one, since this was 2 standard deviations above the mean, let's go all the way down to 2 standard deviations below the mean. This area right here, according to the empirical rule, or the 68, 95, 97 rule, this was 95% between 2 standard deviations, right? That means how much left over is there in those two tails? Well, it's got to be the leftover 5% to make 100%. But 5% is for both of those tails combined, and I only want to know the right tail. Now, the nice thing about the normal distribution again is that it is symmetric, which means these two tails are the same exact size. So take our 5%, cut it in half. This tail has 2.5%, and this tail contains 2.5%. So what percent of readings are undesirable? 2.5% are undesirable. So notice, I'm using the 68, 95, 99, 7. You have to use those numbers, the 68, 95, and we didn't do a problem that involved the 99, 7, but hopefully you get the idea after using the 68 and the 95. Now, the last problem here contains 3 different problems. I want you guys to try this one on your own now, since we're at the end of the video. Try these 3 problems out. I'll check them tomorrow for credit during class, and we will also go over them to make sure that you really understand what's going on. But you should be able to use the empirical rule for all 3 of these problems. Adios, goodbye, and good luck.